Voyager 1 and Voyager 2 are the most distant objects ever built by human hands. Two old probes, the size of a small car, hurtling through the dark on a journey that began before the first personal computer landed on a desk. They have been flying for nearly 50 years. They have crossed planets, oceans of radiation, and the boundary of our own solar bubble. And right now, at this exact moment, they are slowly going dark. Their plutonium-238 power source is decaying year after year, losing about 4 watts every 12 months. The team at JPL has already had to shut down 8 of the 10 original instruments on Voyager 1, with the most recent shutdown happening in April 2026, when the low-energy charged particle instrument was turned off to keep the spacecraft alive. Voyager 2 lost the same instrument back in March of 2025. After that, only 2 science instruments remained operational on each probe, and the team is racing against the clock to keep them running. The countdown to silence has begun, so a lot of you have been asking the same question in the comments. Where's Voyager 3? Why isn't NASA already out there with something better, something faster, something that won't take half a century to reach the edge of the solar system? With everything that has changed technologically since the 70s, why are we still depending on 2 probes that ran their first computer on 69 kilobytes of memory? Folks, I have news for you. Excellent news, actually, because the answer is not we are working on it. The answer is we are, right now. In the laboratories of the Johns Hopkins Applied Physics Laboratory, in partnership with NASA, a real successor to the Voyagers is taking shape. It does not officially carry the name Voyager 3, but in terms of ambition, scientific hope, and sheer audacity, that is exactly what it is. And the engineering being poured into it is going to push humanity past the heliopause, faster than anyone thought possible. Today we're looking at what this mission really is, where it is going, how it plans to fly, what it will carry, and what it could find, and why, if we are smart enough to actually fund it, it could leave Earth in our lifetime. So stick around, because the new Voyager 3 is much closer to reality than you think. Before we talk about the future, we have to settle a small piece of history, because technically, a Voyager 3 did exist on paper. Back in the late 1960s, when NASA was first sketching out what they called the Grand Tour, the original plan was 4 probes, not 2. 2 would fly the Jupiter, Saturn, Pluto route, and 2 would fly the Jupiter, Uranus, Neptune route. It was going to be the most ambitious robotic mission in history, a 4-spacecraft cascade across the entire solar system. That plan got slashed. Budget cuts, shifting priorities, the Apollo program eating most of the agency's funding. By the time the mission was officially approved in 1972, it had shrunk down to 2 spacecraft, the ones we know today, and those 2 had to do everything the original 4 were supposed to do. Voyager 1 and Voyager 2 are essentially the survivors of a much more ambitious dream, scaled down to fit a congressional budget that nobody wanted to fight over. Now, why is this important? Because it tells you something crucial about why we can't just build another Voyager today. The Voyagers only worked because of one specific, rare, cosmically ordained thing: the grand planetary alignment. In the late 1970s, the 4 giant planets of the solar system were positioned in a configuration that allowed a single probe to visit all of them in sequence: Jupiter, Saturn, Uranus, Neptune, one after another, like gates in a cosmic slalom. Each planet's gravity captured the probe toward the next. This configuration happens roughly once every 175 years. The last time before 1977 was in 1801. The next will be around 2150. Gary Flandreau, a young NASA scientist at the Jet Propulsion Laboratory, worked out the math in 1965, and from that moment, NASA had roughly 12 years to build something and launch it. After that, the train left the station for nearly 2 centuries. So when people ask, why don't we just build a better Voyager and send it out the same way? The honest answer is we can't, not the same way. The planets are not in the right positions anymore. Every decade that passes is a decade in which the alignment degrades further. We can't repeat the trick. If we want to get out there at a reasonable speed, we have to use a completely different method. And that is where the real Voyager 3 enters the story. Okay, people, here is where it gets serious. The mission I am about to describe is a real NASA-sponsored concept study that has been running for years at the Applied Physics Laboratory of Johns Hopkins University. Its official name is the Interstellar Probe, and it is, in every meaningful sense, the spiritual successor to the Voyagers. The team behind it is led by Ralph McNutt, a veteran heliophysicist who has spent the last decade making sure this concept gets the engineering rigor it deserves. The study has involved more than 445 scientists and engineers from institutions all over the world, contributing thousands of hours to trajectory analysis, thermal modeling, instrument design, and propulsion studies. Nothing about this is a back-of-the-napkin idea. This is the most carefully studied deep space mission concept of the past 2 decades. And what they have come up with is a spacecraft that would launch sometime between 2036 and 2041, ride a heavy lift rocket out of Earth orbit, swing past Jupiter for a gravity assist, and then aim for one of the most ambitious destinations ever proposed: 1,000 astronomical units from the Sun. To put that into perspective, Voyager 1 right now is sitting at about 163 astronomical units from home, and it has been flying since the year of the original Star Wars release. The Interstellar Probe is being designed to go more than 6 times farther than Voyager has reached in nearly 50 years, and to get there in roughly the same amount of time. How? That's the part that gets every space engineer in the world a little dizzy. Because the Interstellar Probe has to solve a problem the Voyagers never had to face. There is no planetary alignment to exploit. The window closed decades ago. So the team has been studying 3 different trajectory options, each one more aggressive than the last. The first option is the simplest: launch hard from Earth, fly past Jupiter for a single gravity assist, and ride that boost out into deep space. This is the conservative plan. It would get the probe moving at 6 to 7 astronomical units per year, which is roughly double the Voyager speed. Still extraordinary, still capable of reaching the heliopause and pushing beyond. The second option adds a powerful burn during the Jupiter flyby, gaining additional velocity at the cost of more complex engineering. But the third option is where the team really lets the engineers off the leash. It is called the Solar Oberth Maneuver, named after the German rocketry pioneer Hermann Oberth, who theorized its basic principle back in 1929. The idea is to send the probe diving in toward the Sun, and I mean really close, with 3 to 4 solar radii, which is something like 1.3 to 1.9 million miles from the surface. That is closer than any spacecraft has ever flown except the Parker Solar Probe, and it is hot. We are talking surface temperatures around 4,500 degrees Fahrenheit, hot enough to melt steel like butter, and hot enough to make conventional rocket fuel explosively unstable. And here is the genius of the maneuver. Right at closest approach, where the spacecraft is moving at maximum velocity thanks to the Sun's gravity, you fire the engine. That tiny push at that exact point gets amplified by the Sun's gravitational well into a massive escape velocity boost. It is one of the most elegant tricks in all of orbital mechanics. You are essentially using the Sun itself as a slingshot, just like the Voyagers used Jupiter and Saturn, except the Sun is more than 1,000 times more massive than Jupiter, so the boost it provides is on a completely different scale. Voyager 1 is currently moving at about 38,000 miles per hour, which translates to roughly 3.6 astronomical units per year. The Interstellar Probe with a full Solar Oberth could hit something like 20 astronomical units per year, about 212,000 miles per hour. That is more than 5 times faster than anything humanity has ever launched into deep space. 5 times faster than anything humanity has ever flown. That number alone reshapes what deep space exploration can mean in a single human lifetime. Now, the Solar Oberth is the dream scenario. It is also by far the hardest one. The heat shield required to survive that close to the sun is at the absolute bleeding edge of current materials science, being developed right now by a team under materials scientist Jason Benkowski at APL. His group is working on an unconventional approach that uses the sun's heat itself as propellant, passing helium gas through a specially coated heat shield to generate thrust. If it works, it would be the first time anyone has ever turned solar radiation directly into deep space propulsion. If it doesn't work, the backup plans are still impressive but slower. Either way, the Interstellar Probe is being designed to operate for at least 50 years after launch, possibly 70 or more. Its RTGs will use next-generation americium-241 isotope technology, more efficient than the plutonium-238 of the Voyagers. Its onboard computers will have more processing power on a single chip than the entire Apollo program had across all its hardware. Its antennas will use optical laser communication in addition to radio, which means the data we get back will be a real, continuous stream of high-quality science rather than the trickle of bits the Voyagers were forced to send. None of this is science fiction. We are talking about hard engineering being done right now by people whose business cards say propulsion engineer, thermal protection specialist, or interstellar mission designer. The Interstellar Probe is not waiting to be invented. It is waiting to be funded. Okay, but let's get to the part that really matters. Why? Why are we spending billions of dollars and decades of engineering effort to send a probe 1,000 AU from the sun? What is exactly out there worth the trip? The answer is because we are blind. Genuinely scientifically blind to most of what is happening at the edge of our own solar system. And the new Interstellar Probe is being designed to fix that. Think about this. The Voyagers gave us our first real measurements of the heliopause, that boundary where the solar wind from our sun crashes into the interstellar medium of the galaxy. Voyager 1 crossed it in 2012. Voyager 2 crossed it in 2018, and those are the only 2 points of data we have on the entire structure. 2 pinpricks on a frontier that wraps around the entire solar system in every direction. It is like trying to figure out the shape of a basketball by touching it in 2 spots. You get a rough idea, but you miss an enormous amount of critical detail. And the Voyagers were carrying 1970s instruments. Plasma sensors, magnetometers, particle detectors, all built with technology that was already obsolete by the time the spacecraft reached Saturn. They sent back data that was revolutionary in its time, but compared to what we can build today, the resolution was crude and the sensitivity was a joke. Modern detectors operate at a level of precision the Voyager engineers would have considered physically impossible. The Interstellar Probe will carry roughly 9 to 10 cutting-edge scientific instruments. Modern magnetometers with sensitivity orders of magnitude beyond anything on the Voyagers. Mass spectrometers capable of measuring the chemical composition of interstellar dust grain by grain, telling us what the material between the stars is actually made of. Particle detectors that can resolve the energy spectrum of cosmic rays, with a precision that would have been pure fantasy in the year of the Voyager's launch. Imaging instruments designed to map the global structure of the heliosphere in ultraviolet light. Plasma wave detectors that listen to the sound of the interstellar medium itself, which has its own faint hum that the Voyagers detected only after their main plasma instruments had already started failing. We will go from sketch-quality data to high-definition science across the entire frontier. But here's the truly mind-blowing part. By the time the Interstellar Probe has passed the heliopause, it will be able to look back at our own solar system from outside the bubble. And for the first time in human history, we will see what our cosmic home actually looks like from the outside. Not through models, not through inference, through direct observation with instruments designed specifically to map the global structure of the heliosphere from a viewpoint no human-built object has ever occupied. For the first time, we will get the global shape of the heliosphere and finally know whether the long-standing teardrop model is correct, where the bubble has a long tail pointing away from the direction of solar motion, or whether one of the more exotic croissant-shaped models that recent simulations have proposed is closer to the truth. The Quasar model, proposed by Mirav Ofer and her collaborators at Boston University, comes from advanced magneto-hydrodynamic simulations that include charge exchange between solar wind ions and interstellar neutral atoms. It predicts a heliosphere that looks nothing like the comet tail we drew in textbooks for decades. Which model is correct, or whether the real shape is something nobody has yet imagined, can only be answered by going there and measuring it directly. The probe will measure how the interstellar magnetic field deforms our protective bubble. It will sample the local interstellar cloud our solar system is currently passing through, the so-called local interstellar cloud, with instruments still operating inside that cloud and continue to operate after crossing beyond it. The result is going to be the most three-dimensional view of our solar neighborhood ever obtained. And on the way out, we get bonus science. The probe could potentially fly past one or more dwarf planets in the Kuiper Belt. Quaoar is on the list, sitting roughly 43 AU from the Sun, with a small ring system that nobody fully understands. Orcus is on the list, a Plutino with its own moon. There are dozens of other Kuiper Belt objects that might be in the right position depending on the exact launch date, and there could easily be objects we have not even discovered yet hiding in the dark, waiting for the probe's instruments to find them. Every one of these flybys would be a New Horizons level event in its own right. Now, I want to push this a step further, because while the Interstellar Probe is the closest thing to a real Voyager 3 we have, there is a sister concept being studied at the same time that is, frankly, even crazier. And once you understand what it could do, you start to see why the second half of this century is going to be an extraordinary time for deep space exploration. It is called the Solar Gravitational Lens mission. The basic idea uses one of the wildest predictions of general relativity. Albert Einstein showed in 1915 that mass bends light. Every massive object curves the fabric of space-time around it, and light traveling near that object gets deflected by the curvature. The sun, being heavy, bends light coming from behind it, and if you go far enough out from the sun, 547.6 astronomical units, the bent light from a star directly behind the sun converges into a focal region. The sun, in other words, becomes a gigantic natural telescope, a lens hundreds of millions of miles wide, sitting in space free, already built, just waiting for us to use it. The numbers on this lens are not normal numbers. The brightness amplification at the focal region is around 10 to the 11th power. We are talking 100 billion times the light from the original source. With a 1-meter telescope sitting at the focal region of the Solar Gravitational Lens, you could take a direct multi-pixel image of an Earth-like exoplanet up to 100 light-years away. Not a single dot of brightness, not a smudge, a real image with surface features, continents, oceans, possibly clouds, surface revolution of about 10 to 25 kilometers per pixel. Enough to see the shape of continents, the position of weather systems, signs of vegetation if there is any, signs of cities if there are any, continents on an alien world, mapped by a probe we could potentially launch this century. Just sit with that idea for a moment, because it is the single most extraordinary scientific possibility on the table right now in all of astronomy. We would not just confirm that life exists on other planets, we would be able to see the geography of those planets, identify oceans and weather patterns, look for the spectroscopic fingerprints of biology in the atmosphere with a resolution that traditional space telescopes could never achieve, no matter how big we build them. And here is the beautiful part of the physics. When you sit at the focal region of the Solar Gravitational Lens and you look back toward the sun, the light from your target exoplanet does not come at you as a single point. It arrives as a thin ring of light surrounding the sun, what general relativity calls an Einstein ring. Every pixel of that ring contains light from a different point on the exoplanet's surface. By moving your spacecraft slowly through the image plane and recording the ring at each position, you can reconstruct the entire surface map of the planet, one slice at a time. It is image processing on a scale nobody has ever attempted, and the math works out so beautifully that NASA's innovative Advanced Concept Program has now funded multiple phases of feasibility studies confirming it is doable with technology we are actively developing. The Solar Gravitational Lens mission is a separate concept from the Interstellar Probe, but the engineering challenges overlap massively. The two missions share the same fundamental problem. How do you build a spacecraft that can travel hundreds or thousands of astronomical units while keeping power flowing for decades on end? Solving that problem for one mission essentially solves it for the other. The Solar Gravitational Lens team, led by Slava Turishev at JPL, has been studying a swarm architecture using small satellites with solar sails, designed to reach the focal region within 25 years of launch and operate there for at least another 10 years, as they sweep through the image plane and reconstruct the full picture pixel by pixel. If both missions fly, the Interstellar Probe in the late 2030s, the Solar Gravitational Lens in the 2040s or 2050s, the second half of this century could become the era when humanity finally sees its galactic neighborhood for what it actually is. No abstract dots in a Hubble image, not interpretations of spectra from a distant transit, real, resolved, three-dimensional knowledge of the worlds around us. And now we get to my favorite part, the cultural part, the part that makes engineers roll their eyes and dreamers light up. Because every conversation about Voyager eventually comes back to the same beautiful object. The Voyagers carried something called the Golden Record, a copper disc, gold-plated, mounted to the side of each spacecraft. On it, 116 images of Earth, greetings in 55 languages, music ranging from Bach's Brandenburg concertos to Chuck Berry's Johnny Be Good, the sounds of whales, of thunder, of a mother kissing her child. Carl Sagan and his team chose those contents in 1977 as humanity's letter to whoever or whatever might one day find the probe drifting in the void. It was a snapshot of who we were at that moment, sent into the dark as a kind of cosmic message in a bottle. The team had only 6 weeks to pull the whole project together before launch, and Sagan later wrote that the entire process felt almost reckless in its compression. They argued about which composers belong, which languages to include, whether to add the sounds of war or only peace. They settled on peace, in case the message was ever decoded by something out there capable of understanding it. They left the Earth's address on the record too, in the form of a pulsar map that pinpoints our solar system relative to 14 nearby pulsars, each one a kind of cosmic lighthouse with a unique flashing signature. Now, the official Interstellar Probe study does not include a golden record. The team is focused on science and engineering, and rightly so, because every gram of mass on a deep space probe costs millions of dollars in propulsion. But the question gets asked at every conference, in every public talk, in every magazine feature about the mission. If we were to put a new message on a Successor probe, what would it look like in the 2020s or 30s? Some of the speculations are wonderful. Modern crystalline data storage could hold the entire language Wikipedia, every classical music recording ever made, high-resolution images of every species on Earth, the complete sequenced human genome, the Voyager Golden Record itself as a recursive reference, and probably most of the major films and books of the last century. Holographic storage techniques being developed at places like Microsoft Research under the codename Project Silica can write data into fused quartz coins using femtosecond lasers, and similar work at the University of Southampton has demonstrated 5-dimensional optical storage with densities of hundreds of terabytes per disk. That coin could survive for billions of years. Longer than the Earth itself will remain habitable. A small crystal riding on the side of the Interstellar Probe could contain essentially the sum of total human knowledge as it stood at the moment of launch. A library small enough to fit in your palm and durable enough to outlive Earth itself. And here is what gets me. The Voyagers carried 1977 Earth, a planet that had just gotten its first personal computers, that was still listening to vinyl, that had never seen an image of a black hole, that did not know whether there were planets around other stars. The new probe would carry a very different Earth, a planet that has discovered thousands of exoplanets, photographed the event horizons of black holes, sequenced its own genome, built artificial intelligences capable of writing poetry and code, mapped its own brain, its synaptic resolution, and finally decided to look beyond its own solar bubble with serious intent. That is the message worth sending. That is the snapshot worth preserving. Okay, folks, let's be honest with each other. Let's not pretend everything is rosy. The Interstellar Probe, at this exact moment, is still a concept study. It has not been officially funded as a flight mission. It is in the queue, waiting for NASA's Heliophysics Decadal Survey to formally rank it among the priority missions for the next decade. That ranking will determine whether the project gets the billions of dollars in funding it needs to actually fly, or whether it sits in a JPL filing cabinet alongside dozens of other beautiful concepts that never made it past the drawing board. There are competitors. There are budget pressures. There is the eternal political question of whether long-term science investments can survive the short-term cycles of government appropriations. The Interstellar Probe team has been working on this concept for over a decade already, and they could be working on it for another decade before launch is even formally approved. That is the brutal reality of frontier space exploration in the 21st century, where every mission has to fight for survival against fiscal headwinds that have nothing to do with science. But here is what I want you to understand. The technical foundation already exists. Trajectory analysis has been done in painful detail. Instrument concepts are mature. The heat shield research is being actively funded under NASA's innovative Advanced Concept Program, and the Americium-241 power source is being developed by the European Space Agency. The Solar Oberth Maneuver has been studied to a level of detail that makes it look genuinely doable, not just plausible. What this project is waiting for is not a scientific breakthrough, but a checkbook. And history suggests that the checkbook eventually opens. Voyager itself took years of political fighting before it got the green light. The James Webb Space Telescope took decades from proposal to launch, surviving multiple cancellation attempts along the way. Parker's Solar Probe took roughly 50 years to go from a concept paper to a real spacecraft sitting in the sun's corona. Big space science is slow, and big space science is expensive, but big space science also happens. The pattern is consistent across the history of the agency. If I had to bet on it, and this is just my read of the situation, not an official prediction, I would say the Interstellar Probe gets approved within the next 10 to 15 years, gets built through the late 2030s, and launches before 2045. By the time it crosses the heliopause and starts the looking back phase of its mission, most of you watching this video right now will still be around to see it happen. And what we will learn from it, what we will see when those first images come back from beyond the bubble, will be one of the defining scientific achievements of this century. The Voyagers are dying, the new one is coming, and it will see things the old ones never could. So that is the real Voyager 3, folks. Not a sequel, not a copy, a successor. A probe being built for a different solar system than the one Voyager knew. Because the planets have moved, our technology has moved, and we have moved. Half a century after the launch of the original probes, we are about to send the next one. And if everything goes the way it should, we are about to learn more about the edge of our cosmic neighborhood than we have ever known before. And here's my question for you. If you could put one thing on the new golden record, just one, a song, an image, a sentence, a piece of code, a recipe, a memory, what would you choose? What is the one thing about life on this planet right now that you would want some distant civilization to find 100,000 years from today? Drop it in the comments. I'm genuinely curious what you all come up with, because I think the answers say as much about us as the original golden record did. And if you want more deep space content like this, check out our full Voyager playlist. Everything we have made on the original missions, their journey, their legacy, the whole story, all in one place. It's all there waiting for you. Stay curious, folks. The universe is waiting.